Okay, so let's get started. So last time what we got up to was this Mahalanobis transform and Mahalanobis distance. And what they were linear transformations where you take away the mean, and where in standardization you divide by the standard deviation, but so that removes the sort of scale from everything, right? So that everything has correlation, one with itself, and then some correlation between -1 and 1 with everything else. The Mahalanobis transform takes away the correlations as well, right? And that's going to help us think about how the contours of the multivariate normal are shaped. So from comparison of equations 4, 1, 1 and 4, 3, 3, and I'll write those out. So this is that the normal is proportional to x. Yeah. And this is that the Mahalanobis distance is yeah, so comparing these two equations, yeah, we see the contours of the multivariate normal as defined in chapter 3. Yeah. As curves of constant probability density. So a contour is a curve or a surface on which the probability density is constant. Our hypersurfaces of constant Mahalanobis distance. Yeah. This means that for each constant A, there will be a contour. There will be a contour satisfying x minus mu. So that is equal to a squared, right? And so we'll call that 4, 1. Okay. So we're going to refer back to this. Okay. So now, if you remember, so sigma is p by p, positive semi-definite. So we can find eigensystem, and that's a set of eigenvalues and vectors that I from 1 to p. Yeah. With so we went through this bit at the end before, didn't we? Actually, but I thought we'd only got up to Mahalanobis distance. I think we started this. There's no harm in doing this again, is that right? In more detail. Yeah. Because we're orthonormal eigenvectors. So that B I hat dot B J hat is delta J. Yeah. So what I'm going to do is I've realised that there's too many U's knocking around. So the note is printed, I'm going to change, right? And so we're going to let the matrix V, that's going to be a matrix with these P orthonormal eigenvectors being its columns. Yeah. This is orthogonal. Okay. And the way to see that is to consider the matrix like this, where the B's are its rows. Yeah. And how that's going to get multiplied by yeah. So think about this multiplication, and because of this rule here, this is going to be 1, 1, 1. Yeah, little zeros. So that's the P by P identity. Not shifting this with the right. So I'm trying to capture this by recording as well. So does that help? Yeah. Yeah. I'll be moving it around, but if you want to move around in the room, feel free. Okay, so this is equal to V transpose V. Yeah, but we know that then implies that V transpose is the inverse, right? Because a matrix time, the matrix that when P multiplied by this gives you I is the inverse, right? So transposition gives you inverse for an orthogonal matrix. And that's a length preserving transformation. So I won't okay. So I'll just write it down. I'll just write these points down without going through every bit of it. So I'll say the map B that this induces is length preserving. Okay, so I won't go to showing that again. That's as it was in the notes we went through before. Yeah, it's length preserving, meaning it's with rotations and reflections. And the other thing to note is that, let's check this one, so I didn't do this in as much detail. So sigma B is sigma on kind of thing, yeah. And then because of how matrix multiplication works, that's going to be the matrix made up of lambda 1, B1, lambda 2, B2, right, and so on to lambda P, BP. Yeah. And that's going to equal this times the diagonal matrix with lambda 1, lambda 2 to lambda P and zeros elsewhere. Yeah. We think about how that works. So that's going to equal lambda V, sorry. Yeah, that's right. So, yeah, that's going to equal V times this lambda matrix for lambda matrix is there on the lambda i's, yeah. So then the other thing to note, if that's in this bit of the board, is taking this result here, yeah. So sigma B is B lambda. Then we're going to look at take this result here, substitute that in, yeah. This orthogonality, we post multiply by BT. So sigma B BT is B lambda BT, yeah, is sigma. And that's going to imply, and again, I'll just leave that as an exercise to check, because you just substitute in that sigma inverse is B lambda inverse B. Okay. And so what I'm going to do is name this equation here as 40. Again. So now the main thing we're going to use on this for this that we've developed here to show is the contours of a multivariate normal with mean vector mu and covariance sigma are ellipsoids. Yeah. So this is ellipsoids, being the higher dimensional generalization of an ellipse, right? So it's something with this kind of shape of 3D or, you know, yeah. They're ellipsoids centered on mu with axis vectors that are the set A lambda I in P, where and just so you know, this is so hopefully a reminder for everyone, is an ellipse is specified by what are called the major and minor axes, right? And then you have a series of these depending on their length, right? So if I give you two vectors, yeah, at right angles, those are the axis vectors for a 2D ellipse, right? And in higher dimensions, I can keep giving you vectors at right angles, and that will tell you what the ellipsoid is, right? That's enough information to know what the ellipsoid is, right? If you remember, so this is major, you know. So hopefully, yeah, we're going to show that to show what that means, right? Okay. So the equation for contours for 1, okay, and then we're going to substituting for 2 into this. And we're going to obtain this equation, which is that A squared is minus mu transpose on B lambda inverse B transpose X times mu. Yeah. Is Z transpose Z for Z equals B minus mu. Yeah. If you write this out, we know what this is. This is the sum over I equals 1 to P of Zi squared over lambda I. Yeah, because we can work out what the inverse of the diagonal matrix is. It's just the diagonal matrix of 1 over the elements. Yeah, and this is the ui squared. And we'll label this equation 4 for ui is Zi over root lambda I. Okay. So then what we're going to do, then note um, 4 is the equation for a radius A here in the coordinates ui. Yeah. So sum of square coordinates is A squared. They are taking this bit of the equation that I've underlined here. That's the equation for a P sphere. Yeah. Okay, and the Z's the ZI coordinates scale this. So Zi is roots lambda ui, giving an ellipse with the advertised axes. Yeah. So I guess I should say axis lengths, you know. Yeah. You know these things, I'm using arrows here as well. And X is this linear transform on Z's. Yeah. And is a transform And that's the length A. Yeah, so the length A times root lambda I axis. Yeah, that's probably like that more clearly in the notes as well. Yep, into that. And that's by the definition of B. Yeah. Yeah. So you can see that by thinking about B being made like this, and then B acting on something that's 1, 0, 0, 0, you know, yeah, and B acting on something that's 0, 0, and then a 1 somewhere, and then some zeros, right? Because those are that's the basis in O, yeah, and then B rotates it onto this. But we've already scaled these by the length here, right? And followed by, and this is just a shift. Yeah. So what I'm going to do is we'll work this through. Okay. So that may looks a bit abstract. That's kind of sufficient to show what we wanted, right? Which is that it is an ellipse. We've just shown how this equation defines an ellipse as we work back to the original equation. Okay. So now let's do a worked example. So let's take some mu is 2 minus a half. Sigma is 1, 7, 9. Yeah. Okay, so that's our example of a multivariate normal. And this implies, after a bit of work, that we've done this in the problems, that B is 1 over root 2 times 1 minus 1, and lambda, root of lambda 1 is 4/3, and root of lambda 2 is root 2 over 3. Okay. So that's one example. You can derive those things. So let's have a look. Let's draw 4 sets of axes and see how this this develops. Yeah. So how would we work out where's a contour? So we're going to look at the a equals 1 contour, right? So let's look at the construct a equals 1 contour. Yeah. So this is our example. Well, in the use, yeah, the contour is going to look like, yeah, that's the circle equation. Yeah. So this obeys u1 squared plus u2 squared is a squared, right? That's the u contour. Okay. So now let's look at the in the z's. Yeah. So these are the scaled ones. Well, the bigger contour is 4/3. So that's going to have this major axis here. Then the minor one is √2/3. Yeah. And so that's going to go around like this. So that's -1, 1, 1, -1. Yeah. So that's what it's going to look like. This here is what we mean by the major axis. Yeah, this is length 4/3, and this one is length √2/3. Yeah. Then let's look at it in centered coordinates. So let's look at it in coordinates x1 minus mu and x2 minus mu. Yeah. And what that's going to do is, interestingly, well, I've said I have to do this, right, is when you rotate it round, the that same ellipse is going to just perfectly touch the -1 bit here. Yeah. So it's still going to have, because it's rotation and reflections don't really matter, right? You see, because this has a reflectional symmetry, the minuses just don't matter. That's why we didn't specify that the minuses have to go a certain way. But you'll see that because this is length preserving, this axis here is still 4/3, and this one is still √2/3. Yeah. And then finally, there's a shift by the mean, which is going to take the contour to over here. Yeah, so the final contour will look like that, where this is the points to -0.5, and this is just that ellipse but transposed. Okay. So you are expected to know how to construct a contour like this, right? And this is why I sort of, this is useful because we're going to start drawing things like, I suppose, a multivariate normal looks like this or looks like this, right? And it's that I'm trying to draw this kind of ellipse, right? So this is where specifying a multivariate normal. Okay. Okay, so any questions on that, the shape? I know it's very different from all the other stuff we did in stats, because it looks a bit like geometry, right? But this is why I call this geometry of the multivariate normal, that we're worrying about ellipses and circles, but it's the right way to understand going on. Okay, so sorry, are there any questions on that? Yeah, all good. Yeah, I know it's difficult and different from other stuff we do. So now let's try and say something about where the points actually are within that geometry, right? So you've got these contours. How are they actually? What does the aim mean, right? How are they actually laid out? Okay, so the main result we're going to derive, and this is hot off the press, so I'm going to do this differently from this is 4/5. I'm going to do this differently from the notes. The proportion of the population of the multivariate normal within the contour. Right. One is p squared. Okay, so that's our result now. There's a really elegant argument for this. And I used to present that, and people would then look at me and go, yeah, but that's elegant, but you know, what's it all mean? So let's have a go at doing this more explicitly, okay? So let X go like normal sigma, and U be under the half minus 1 B transpose minus mu. Yeah, so we defined this lambda as the half as the matrix square root in foundations. Yeah, and so in the tutorial in problem 4.2, we will see using theorem 4.1, we get if U is standard normal, yeah, the vector of standard normals. And the contour in 4.1 then looks like this. So that's a squared, I'm just going to write this the other way around, is x minus mu transpose sigma minus 1x minus mu. Okay, that's just the equation for 1 with the left-hand side and right-hand side swapped. And this is then equal to sum from I equals 1 to p of u I squared for u equals lambda half minus 1 p x minus mu. We're using moving 4.4, which I may have failed to, I can't remember if I remember to write. So equation 4.4 is, yeah, equation 4.4 is the contour, right? So yeah, we use that. And and we saw that this contour saw that contour was S. Yeah, E minus 1 sphere of radius A. Okay, so what that sphere does, so if you look at it, this is the P sphere. Okay, there's the origin. And what this sphere does is it's the boundary of the ball. So again, sorry about the geometry, bounds the radius A ball. Okay, so we're interested in the density in the ball. And I'm going to call that F tilde because it's a sort of radial density. So it's a distribution function of that, but it's the radial one, it's how far it's going out. So I'm writing, it's associated with the random vector x, but I'm going to put this tilde on it. Yeah, just to show that it's not the same one with that. And it's as we go out to A, so this is length A, right? And what we're doing is we're integrating over this ball, which is what's inside that contour. So if we integral over the ball of a normal distribution, because we've shown that U, like this, is standard normal. So it's a standard normal on the U's given naught I. Yeah. So does that make sense what I've said? Right? We've got a contour. The contour in some change of variables U is a sphere. And we're integrating from the origin up to that sphere and trying to work out how much of the distribution is in that ball. Okay. And just quickly, we'll just note that this here is going to be, this is going to look like x minus x minus a half of u1 squared plus u2 squared plus b squared, yeah, and I'm going to call these r squared, right? Because what we're going to do is do this in polar coordinates, right? So we're going to try to transform to r theta, yeah, polar coordinates. So there's p minus one of these. So, you know, in general, you can transform Cartesian coordinates to polar where there's a radius and a load of angles, right? We're not going to care what the angles are. So this is the integral from r is 0 to a. The integral, and then at each one of those, the integral over the p sphere. So what we're doing is we're going out in little shells, and each shell is size r. Yeah, each shell is a p sphere of size r. And we integrate over the those p minus one angles in each of the little shells. That's a p minus one sphere. Okay, and then we're going to substitute in the normal distribution, which is 2 pi the minus p over 2, and then this substitution for minus a half r squared dr. Okay. So what we've done is we've said this sum over u squares, which is going to come here. Yeah, it's going 1 over the 2 pi p. Yeah, which I've just written here is more of a function, you know, to avoid too many fractions. Yeah. And then this here is just the surface area of the radius r p minus 1 squared. Yeah, and that's well known. That is the integral from r equals 0 to a of 2 pi p over 2 divided by the gamma. In fact, the gamma function. Yeah, if you don't know what a gamma function is, don't worry. It's just a function that turns up in the integration of the sphere. Then r the p minus 1. Yeah. Then we're multiplying by 2 pi to minus p by 2 e to the minus r dr. Right. So that's where we've got to with the FA. Okay. Okay, so now let x be r squared, so r is x to the half and dr is a half x to minus a half. Then in those coordinates, f tilde x of a is the integral from x is 0 to a squared. Yeah. Or then we've got a, if you notice, these are going to cancel. Yeah, so we're going to cancel those straight away. And so that leaves us with a 2 on top. Yeah, over 2 to the p over 2 and the gamma and p over 2, then x p minus 1 over 2 e to the minus a half x x minus a half x. Yeah. And then cancelling all of this, simplifying all of this, we're going to get this the integral from x equals 0 a squared of x to the p over 2 minus 1 e to the minus a half x over 2 p over 2 gamma over 2 the x. Then this here, okay, this is the PDF of I squared p random variable. Yes, so C sample 1 for 3b. And so this the integral of, so this thing here is equal to the actual f of pi squared p evaluated with a squared. Yeah, is that, and that's what we were trying to show. Yeah. By how we defined normal f without the filter on it. Okay. So that's a good place to get to, but I will just note a couple of things. Okay. Got a couple of minutes, so let's note some things. So note one thing to note is just by out of interest, a squared equals 5.99 is about 95%. Yeah. So you know, the 95% confidence interval, the 95% confidence region is going to be an ellipse with a equals about, you know, a squared is about 6. Yeah. The other thing to note is we've shown pi squared as sum of u squared and its PDF are equivalent. Yeah. So some people define the pi squared as the sum of normals, then derive the PDF. We defined it as the PDF and then said, oh, that PDF comes to the sum of normals, right? So we've shown that those two things are equivalent, sort of incidentally, right? But the other thing is the alternative route is to pick x randomly from the normal with mean and sigma. Yeah. Then the a squared is yeah, equals the sum from I equals 1 to p ui squared, and that So these are now random variables, right? And we showed that the UIs were all standard normal. So we know that that's chi-squared NP, yeah. So you could always just write this down in 2 lines, go and pick it randomly and do this. And I'd say that because I've got to only take the writing for 2 lines, and you could look at like how can that be right? Right. And it is if you think about it. So go and think about this. So you can just like this is right. That you, if what you do is you've got something here and you pick randomly, you go right. I pick my x sort of randomly according to the multivariate normal law. Then what's the chance that I pick this given value of a squared? Well, that's a chi-squared, right? When you think about it, that tells you that the area within, that the amount of them within that region has to be chi-squared, right? But you're either going to see that or you're not, right? Whereas this thing here, the reason I've changed what's in the notes from this short but rather subtle argument to this rather explicit one is that you can always just follow this explicit one point by point as calculus and geometry, right? Whereas this argument here is very, very elegant when you get it, but it's yeah, you're either going to see or you're not why that's relevant. So those are 3 things to know. Okay, so